Hello and welcome to this lecture of the course Elements of Mechanical Vibrations. We have been discussing the continuous system as it applies to the vibrations of a string, vibrations of a bar, but the most important of the structural elements is a beam, and therefore, we extend our discussion in investigating the vibrations of a beam by first understanding how the governing equations of motion for a beam whose stiffness and mass parameters are distributed as a continuous function of the spatial variable. Okay, so the way we discussed vibrations of a stretched string and that of the bar. Okay, so the way we discuss the vibrations of a continuous system like a stretched string or a bar, undergoing longitudinal vibrations, we are now set to discuss the lateral vibration of a beam. Okay, so the beam can be of any cross section, but when it is perturbed in the lateral direction, it executes what we all know as bending vibrations or lateral vibrations. So, take the case of a turbine blade, which under the action of the fluid forces would execute bending vibrations. Okay. So, this can be treated like a continuous system, and as we always do, our x axis is along the length of this continuum. This axis is y, and pretty much the same way as we did earlier, we take a small very small element of length dx from this particular continuum and focus on the force balance of this small element. Right? So, in that sense, we can consider this small element of length dx before it bends, and look at all the forces which are acting on it. Of course, the beam is also, as we always assume, subjected to external forces. These forces could be due to external loading on the beam, which could be dynamic. That's why it is a function of time and both position. Okay. So, if we take this small element, then the deflection or deformation of this segment at its end, which is located at x distance, may be defined as w x comma t, and at after a distance dx, x plus dx, it has certain other incrementally small increase in the lateral deflection. Now, apart from this external force, of course, there are internal forces which are set up on this element, which we shall define here. This is basically the shear force at position x, and the corresponding bending moment here, and the bending moment at the other side is going to be slightly different than on the left side. So, we define it as, or denote it as, m plus dm, and this one as v plus dv. So, as it vibrates, it would have its own inertia. So, the mass of this element will be mass of this element is going to be rho a dx. A is of course the cross sectional area, and more appropriately, I think we should, in a general case, say that this is rho ax. So, rho is the density of the beam material, and it is assumed constant, but as if you want to make it very general, then you can also assume it to be varying with x. But we know that mostly the beams are of the same material, homogeneous throughout its length, so rho can be constant, but the cross sectional area need not be a constant, as it is the case with most turbine blades, where the cross sectional dimensions do vary along the length x. So rho ax dx is the total mass of this element, and if we want to apply the Newton's second law here for the vertical vibratory motion, we can write this as rho a x dx, mass times the acceleration. So in this case, the lateral deflection and the vibratory displacement is wx comma t at x point, which we can treat as the reference point, and then write the acceleration of this entire element to be dou to wx comma t dou t square as the acceleration of this infinitesimally small element. And this mass times acceleration obviously would have to be equated to the net force acting in the direction of that acceleration. So w and w double dot are along the y-axis, and the net vertical force in that direction would be obviously v minus the other shear force is going to be v plus dv. Okay, so with this what we can write is rho ax dx dou to w, and now for the sake of brevity I am just dropping x comma t. It is understood that w, the vibratory displacement, is both function of x and t. Now here it would obviously be minus dv. Now a small incremental change in the shear force can be approximated as dou v by dou x dx. In the small elemental length dx, the change is going to be dou v by dou x into dx. That's how this equation is leading us to. Now if you take the moment balance about this point, okay, for an element which is under the action of all these forces, we could of course we'll have to see this as if clockwise is considered positive, then the moment m will be the first of the the moments about this point O, and then minus of m plus dm is the other one which is coming from here. Of course you can also take the moment because of the external force fx t, and of course it is dx because this is the external force per unit distance. This we have been using as a standard way to prescribe the external force f of x comma t, which is force per unit length, or per unit length I must say. Okay, so f of x comma t dx would be the total force which is going to act on this element, and we can take that it is we can assume it to be acting, the total force can be assumed to act at the center of this small element, and therefore the moment of this force is going to be dx by 2 into f of x comma t into dx, right? And of course then you have plus v plus dv this is the force which is going to create a moment, and that moment arm is going to be dx. That's how we will write the moment balance here. Okay, so this is equal to 0. What we can do is express this incremental change in the moment and shear force as we have been doing, the way we have done it here as well, that I can write this as minus this m cancels out and dm can be written as dou m by dou x dx. And what we are also going to assume is that dx being very small quantity, the product dx and this dx would be negligibly small quantity, and therefore this second term can be neglected. On similar lines, I can write this as v dx, and although I can write this dv as dou v by dou x dx, since it is again going to get multiplied by dx, I can also ignore this particular term, and then what I am left with is the expression v is equal to dou m by dou x. So that's the relation which we are all aware of, nothing great in this, but we also know the moment, the bending moment is related to the lateral deflection through this expression. So I think keeping it consistent with the parameter we have here, which is w, this is basically the well-known relationship that you are aware of. So the bending moment is related through the flexural rigidity EI, and therefore I must again consider the area moment of inertia of the beam about its neutral plane as Ix. That means the cross-sectional dimensions, as we have assumed to be varying with x, I should also be a function of x. So assuming the mass properties like the density and Young's modulus are constant throughout for the same material, we may write m is equal to Eix dou 2w by dou x square. With this I can write v as dou x of Eix, okay, that is I at a position x, dou 2w by dou x square. It is implicit here that w is a function of both x and time. Alright, with this I can use this equation number 2 in this equation number 1, and then write this as rho ax dx I can cancel out throughout, and then I write this as dou 2w by dou t square equal to so v is what I have here. So if I substitute that in here, it becomes minus of dou x, and in fact that becomes dou x square of Eix dou 2w by dou x square. So now this actually is your governing equation of motion. What we missed out is addition of the external force term here, f of x comma t dx. Okay, so I'm sorry, this should have been added here, f of x comma t dx, and so let us modify this as a general case, x comma t into dx. So therefore we add to this f of x comma t dx getting cancelled throughout. Yeah, so this is now our governing equation of motion for lateral vibration of a beam. Okay, There is no restriction in terms of the cross sectional properties. They can vary continuously with x, and therefore cross sectional area and area moment of inertia of the beam about this plane. So supposing that if this beam is a square cross section, so that you define this as your y axis, as we have seen, this itself is now going to be x, and this is let us say z, then it is going to be IZZX. Okay, so the area moment of inertia will be about this neutral plane. Okay, as we always do, this is a general expression. Sorry, this is the governing equation of motion including the external forcing function. But if we want to now investigate the free vibration response, we could ignore the external forcing term and focus on the free vibration case. In that situation, the equation number 3 would be rho ax dou 2 w by dou t square plus dou 2 dou x square e I x dou 2 w dou x equal to 0. I think that is our governing equation of motion for free vibration. Okay. Now we make one more assumption, that the beam is uniform. Now uniform beam meaning that A is constant. A as well as I, both of them are constant throughout, which means that the beam has the same cross-sectional dimensions throughout. Okay, so it doesn't vary with x. With that assumption only, if we proceed further, we will have a solvable solution, solvable governing equation. Otherwise, this is going to be a complex exercise to solve it for w. Okay, so let's see, by making this assumption of a uniform beam, we write this as rho a now, dou 2 w by dou t square plus, now I can take this EI out, and then this becomes dou 4 w by dou x for 4 equal to 0, right? And I can now formulate this equation into this form. I can write this as plus c square dou 4 w by dou x4 equal to 0. Okay, where c is equal to square root of EI over rho into A, right? So that is your constant c. Now the way we do always, we assume the solution here to be given by wx comma t. The total solution here is given by product of two functions, one independent in x, the other independent in time. Okay, now when we do that, this turns out to be, the first term gives us capital X d2 capital T by dt square, because this becomes an ordinary derivative now, plus c square d4 x by dx equal to 0. Of course, this is to be multiplied by capital T, right? I can reform this particular equation, that is capital X d2t over dt square plus c square capital T d4x by dx4 equal to 0. What we can do is I can write this as 1 over capital T d2t by dt square equal to minus c square by capital X d4x by dx4, right? And so because each of these terms are a function of only one variable and two different variables x and t, and if they are individually equal, which actually means that I can equate it to a variable, a constant, and I will treat this constant as minus omega square. Okay. So by using this, we already know that I can write the first term, that is d2t by dt square equal to minus omega square capital T, which actually gives me a familiar form d2t by dt square plus omega square into t equal to 0. This is our first equation in time. And what do you get by the second equation? This is going to be d4x by dx4, right? This you get as c by omega whole square, right? Okay, so this is, so you get this as omega by c whole square into x equal to 0. Now omega by c I can write this as beta raised to power 4, okay, and which will give us the expression for omega as c square, which is ei upon rho into a. You may notice that we have written c square as ei upon rho a based on our wave equation, and so therefore omega square is going to be c square, which is ei upon rho a into beta raised to power 4. And that basically gives us the expression for omega as beta square root of ei upon rho into a. Now beta is a constant value here. Now this is easily solved. So t as a function of time would obviously be some, I can write this as c1 cos omega t plus c2 sin omega t as a standard solution for the differential equation. And so that's the time function, and the x dependent function, that is capital X, will have to be now written, and x as a function of x here. So we will write this capital X as c e to the power sx as the standard solution to this equation. Okay. If we assume the solution of this particular equation as x of x is equal to c e to the power sx and substitute that in that equation, we basically get c as an assumed constant, s raised to power 4 because it is the fourth derivative here, e to the power sx minus omega over c whole square, and this capital X is essentially C e to the power Sx, as we have assumed, equal to 0. Now, which actually means that S4 is equal to omega over C whole square. Okay. Now, omega by C whole square has been already assumed as beta raised to power 4. So, this is actually beta to the power 4. And if I now want to know what are the 4 possible roots, S1, S2, S3, S4. So, this is going to be plus minus beta and plus minus j beta. You can see that all the 4 roots are basically going to satisfy this condition, and then the capital X function, or the X dependent part of the total solution. Please make a note, we have assumed a Wx comma t to be capital X, a function in X only, and the product of function in X and function in time as the method of separation of variables, and out of which we have already got the expression for capital T as a function of time, and this particular function is something which we are trying to get, and this exactly is the approach to get the function general solution capital X. Now, this being the possible roots, if I substitute back into this expression the general assumed solution, I can now write this as all the 4 constants. So, I can use the constants as C1 e to the power plus beta x. Okay, so this S is going to be replaced with all 4 possible roots, and so this one is the first term. A general solution will be comprising of all the roots. So, contribution from each one will have to be taken into account. So, minus beta x plus C3 e to the power j beta x and plus C4 e to the power minus. So, let me write this as minus j beta x. Okay, which can be written in an alternate form, which I am going to use as so I am basically going to write this same expression as a cos h beta x plus b sin h beta x. So, you will find that the hyperbolic functions are going to be part of the general solution here. C cos beta x plus d sin beta x. So, this is going to be an alternate form of the same solution, and therefore, finally the complete solution Wx comma t, the lateral vibration response, is going to be a cos h beta x plus b sin h beta x plus c cos beta x plus d sin beta x. This is the function in x, and of course to be multiplied by the time function. So, maybe C1 cos omega t plus C2 sin omega t. In fact, we all know that this entire bracketed quantity can also be written as E cos omega t minus phi. That's another alternate form of writing this particular bracketed quantity, right? But in case of strings and bars, we have used this this form, and therefore one can stick to this particular general solution. But this is a general solution because we still haven't figured out what are the unknown constants A, B, C, D and C1, C2. and we all know that they will come from the boundary conditions, right? So this is the general solution of a beam vibratory response of the for the lateral vibration of the beam W x comma t. Now let us, the way we always do, we would like to get the expression for the frequency and mode shape. So we still do not know what this beta is, except the terms within the square root sign, Young's modulus, the mass density, the area moment of inertia, and the cross sectional area. These are all known for a given beam. Again, what is important is that we are assuming a uniform beam, which means that the properties such as material properties as well as cross sectional properties, they do not change with x. With that assumption, this is the expression that we have obtained. Let us look at now very specifically what kind of frequency equation we can get, and we may begin with a cantilever beam. So it's a fixed free beam, and as we discussed, this is the way we wrote the general solution. In this case, of course, I have used the time function as cos omega t minus phi, but you can use the other one as well. So a fixed free beam, which we know is a beam fixed at one end, free at the other end, that cantilevered configuration. What are going to be the boundary conditions? We all know that this being fixed here, the boundary conditions at x equal to 0 is going to be deflection is equal to 0, and the beam cannot have non-zero slope at the root or the fixed end, right? So the slope and deflection, both of them are going to be 0 at x equal to 0. So that's how we can write W at x equal to 0 is 0 at all times, and the slope, which is going to be dou W by dou x, the slope is going to be 0 at x equal to 0 at all times. What about the free end here? No external loads or external force, and so the shear force and bending moment, both of them are going to be 0. The deflection cannot be 0, need not necessarily be 0 there at all times, and therefore deflection as well as slope. So when the beam deflect at the free end, it can have any arbitrary deflection, lateral vibration displacement, as well as slope. So the only two boundary conditions that we can implement at the free end is going to be shear force equal to 0 and bending moment equal to 0. Now we have already discussed these expressions in the derivation of the governing equation of motion, wherein m was equal to EI, the flexural rigidity, EI times the second derivative of the lateral deflection, dou 2W by dou x square. At x equal to L at all times is going to be equal to 0, and we know that the shear force V is dou m by dou x, and so the derivative of this with respect to x is going to be equal to 0. So these are all the four boundary conditions that we have for a cantilevered beam, and those four boundary conditions should give us all the unknown constants, the four of them that you see in the expression of the response Wx comma t. When you implement these boundary conditions, this is what you will get. The constant may have been flipped here and there, but you can treat these as the general solution, and from here, when you apply these boundary conditions, the four of these boundary conditions, you get this as one of the equation. When you implement that boundary condition, one of the two of the four boundary condition, and another set will give you the second equation. And then when you divide the first one by the second one and cross multiply, this is the frequency equation that you are expected to get. You all know this identity. So cos square a plus sine square a is 1, and you know that cos h square a minus sine h square a is equal to 1. So we used, if we use these identities in the solution process, the frequency equation that you will arrive at is going to be this. Cos beta nl cos h beta nl equal to 1, where beta n is going to be the constant associated with the nth mode solution, because we are now assuming a free vibration response. Individual mode are going to generate a specific beta value, and that is beta n value. So this is going to be a numerical solution. You cannot solve this for a closed form expression for beta nl. So numerically, if you solve for satisfying the LHS equal to RHS, you will find that for the value of beta L equal to this, this expression will give you -1 value on the left hand side. So the equation gets satisfied for beta 1 L equal to 1.875104. Okay. And similarly, this equation will also get satisfied for this value, and for this value of beta L, and therefore they now become the first four values of beta L that satisfies this frequency equation. Now we know what is the expression for beta that we have. We know that the value of beta has been obtained. So omega, the frequency equation was beta square ei by rho into a, right? Whereas this beta 1L, which pertains to the first mode, so this is the first mode first natural mode or first normal mode, beta 1L value that we have got. So what we can do is, this expression for the natural frequency can be reformulated as beta L square, and I can take L inside, and then it will be ei upon rho a L to the power 4, right? And this beta L is going to be substituted with these individual values to get omega n, the natural frequency. So obviously omega 1, or the first natural frequency, is going to be 1.875104. You may cut down on some of the significant digits here, but for more accurate value, yeah, you can choose the number of digits here. So this now becomes the first natural frequency of lateral vibration of a beam. If you substitute for beta L equal to beta 2L, you will get the second natural frequency. If you substitute for this, you will have the third one, and so on, right? You can solve this one to get further values of these beta L, and then if you want to find out the nth mode natural frequency, accordingly the beta L value has to be substituted. But this becomes now our expression for the natural frequency. And of course you can use this particular equation to get the mode shape expression. So the mode shape xnx is going to be by substituting a and b in this expression, by using these two equations that we have got by implementing the boundary conditions, and then it is easy to find that the expression for the mode shape is going to be what you see here, right? Nth mode shape xnx will be given by this, where you will substitute for beta n based on whether you want to take the mode shape for the first mode, then beta n will be beta 1, and then appropriately that value has to be substituted for all these beta n in this expression. Of course, alpha n is given by this expression, so alpha n is going to be a constant for a given particular mode, because beta nl is going to be, let's say for first mode, if you are finding out, then alpha 1 will be obtained by substituting beta nl by beta 1l, and so this number is going to be a constant quantity which will get replaced here. And for different positions x, you can find out what is capital X. So that is going to be your mode shape. So supposing starting from x onwards, you can find out x equal to 0 onwards up to x equal to L, you can get the capital X. If you are trying to find out for first mode, this is going to be capital X of x for the first mode, and that will be of course a function of x. And then you can plot all the values of capital X for each value of x that you choose to, and then plot the entire mode shape. So that is how one can find out the mode shape of a fixed free beam, and those will be looking like what? Yeah, so those will be looking like these. So the first one is going to look like this. As expected, at its root, the value of the response is always going to be 0, and the maximum response you obtain at the free end. The second mode would look like this. So now you can see that there is an additional node which is going to get introduced as no node mode here. So we typically do not consider here this one as a node. Sometimes one may use this also as one of the nodes, but irrespective of whether you treat that as a node or not, strictly speaking, you keep on adding additional nodes as we go to the next mode. So you can see that one mode gets added up here, and if you take the third mode, you will find that there is addition of one more node in the mode shape. This is how the fixed free beam or a cantilever beam natural frequencies and mode shapes are obtained. So it's a bit mathematically more involved as compared to the first two continuous systems that we discussed, the stretched string and a longitudinally vibrating bar. The other example here, we will not go into the entire detail of how this is obtained, but following the first the previous case of fixed free beam, you can now look at a pin-pinned or a simply supported beam. You all know that a simply supported beam will have zero deflection at x equal to 0 as well as x equal to L, and because there is no restraint in the slope at the simply supported ends, so the bending moment is also going to be 0, and therefore these four will now form the four boundary conditions of a simply supported beam. And again, going by the general solution Wx comma t, if you substitute these boundary conditions by taking the derivative of the general solution with respect to x twice and then equating it to 0, solving for a, b, c, d, you can show that the frequency equation turns out to be sine beta L equal to 0, and that basically gives you again the same frequency expression, except that beta L will obviously now become n pi depending upon the value of n that you choose. So in this case, the frequencies are going to be n pi square, and so it is pi square, 4 pi square and 9 pi square and so on. So with respect to fundamental, the normal mode function again is going to be a sine function, and so I can show that first mode is going to be a half sine wave, just like our stretched string. The second mode is going to be a full sine wave and so on. So again you can see that an additional node appears as the mode shape as you go to the higher modes. This is how the beam vibration natural frequencies can be obtained. What is also interesting here when you compare it with the stretched string is that in the case of stretched string, omega n was n times omega 1. That means the higher natural frequencies are integer multiple of the fundamental, and but that is not going to be the case in the case of vibrating lateral vibration of the beam. That sometimes uh, the second natural frequency of the beam, um, even if you take the case of a simply supported beam, the second natural frequency is 4 times the first natural frequency, and the third one will be 9 times, and so on. So they are not harmonics or integer times the fundamental, right? So if the first natural frequency of the beam is 40 hertz, the second one uh, would be 160 hertz, and so on. So this is what we need to learn about continuous systems. We have made simplifying assumptions here, and those simplifying assumptions are essential to get workable expressions for the natural frequencies. And if you consider the beam cross section or a bar cross section to be varying with x, then the solution becomes quite challenging, and that is the reason why the continuous systems are typically uh, you solve it with those simplifying assumptions, and for complicated geometries or geometries which involve continuous change in the cross sectional dimensions, it's difficult to get the closed form solution for the natural frequencies. And um, that is why typically we discretize the way we saw that if this beam was continuously changing in its cross sectional dimensions, then one can get solutions by using discretization method, or by segmenting the total length of the beam into several sections and then using numerical methods to get natural frequencies, of course at the expense of computation cost. But then you can then increase the number of segments, so that within the segment the change in the cross sectional dimensions can be minimized to almost zero, and then close to zero. But that's the situation. There are pros and cons here. These expressions are essentially the most accurate solutions. Of course, we have made assumptions in the beam derivation of the vibration frequency that we considered a simple Euler-Bernoulli beam theory, and therefore we could write m equal to ei dou 2 w by dou x square. But if the beam is stubbier, so that the length to diameter ratio is smaller, then these assumptions may not be valid, or they may give slightly erroneous results. But still, continuous systems are treated as sort of more accurate solutions with which one can compare the results obtained through numerical approach, to be sure that your numerical approach is generating reasonably accurate results. So the summary of today's lecture: we discussed the governing equation of motion and how is that obtained from the basic principles for a bending vibration analysis of a beam. Then we understood how the natural frequencies and mode shapes are obtained by implementing different boundary conditions depending upon how the beam is supported. These are a couple of review questions based on the topic. And these are the answers.